With an investment of only about $1 per person each year to improve access to soap and encourage proper hand washing habits, the world could help protect and save hundreds of thousands of lives. What is remarkable is that the tool capable of creating such a major impact is not an expensive device, but a small bar of soap found in nearly every household. Yet to produce this seemingly simple product, thousands of coconuts must be dehusked, dried into copra, and crushed to extract their oil. The oil then goes through cleaning, refining, reaction with alkali, vacuum drying, granulation, fragrance blending, refining, and stamping under dozens of tons of pressure before becoming finished bars of soap. Join Factron Process as we explore the complete journey of transforming vegetable oil into one of the world's most important cleaning products. In 2020, thousands of flights were canceled, many cities were shut down, and the world's most advanced hospitals entered a battle against a virus known as COVID-19. Yet one of the most frequently repeated protective measures was not an advanced medical technology, but an invention that had existed for more than 4,000 years: soap. But how could a simple bar of soap become such an important line of defense against a dangerous virus? One end of a soap molecule attaches to grease and dirt, while the other interacts with water. The rubbing motion helps separate oils, dirt, and many microorganisms from the surface of the skin, trapping them in tiny clusters before they are washed away by water. For viruses with lipid envelopes, such as coronavirus, soap can also weaken their outer protective layer. For this reason, during the COVID-19 pandemic, the WHO considered hand hygiene one of the most effective measures for limiting transmission. This simple but effective cleaning ability has turned soap into an industry worth more than $30 billion, with its value potentially exceeding $43 billion by 2030. To understand how this familiar product is made, we will follow the complete journey from mature coconuts to fully packaged bars of soap. The origin of millions of coconut oil soap bars does not begin inside chemical laboratories, but across tropical coconut growing regions. Each year, the world produces approximately 62.4 million tons of coconuts, with Indonesia and the Philippines serving as the two largest sources. However, for a coconut oil factory, production volume alone does not tell the whole story. What the factory needs is not young coconuts filled with water, but fully mature fruits whose flesh has become thicker, firmer, drier, and richer in oil. Depending on the farming method, coconuts may be harvested directly from the trees or collected after they ripen and fall naturally. The raw material is then transported to a preliminary processing site, unloaded in large batches, and sorted. Workers remove coconuts with cracked shells, mold, fermentation, or unusual odors. Even a small quantity of damaged material can cause the extracted oil to become darker, develop a strong smell, or contain more impurities. This selection process is more important than many people realize. According to the industrial conversion factor used in this script, approximately 8,000 coconuts are needed to produce 1 ton of crude coconut oil. For that reason, every coconut that remains must be sufficiently mature, clean, and consistent in quality before continuing through the production line. The coconuts are fed into a specialized dehusking machine, where serrated rollers grip, pull, and tear away the thick fibrous husks. Some industrial systems can process approximately 2,500 coconuts per hour. The separated fibers are cleaned and sorted for use in ropes, mats, or growing media. The dehusked coconuts then pass through a shell-breaking machine to expose the white meat inside. Damaged sections are removed, while the acceptable coconut meat is chopped into evenly sized pieces, allowing heat to penetrate the material more quickly and consistently. Next, the coconut meat travels through a conveyor drying system more than 100 feet long. High-powered fans blow hot air at approximately 175 degrees Fahrenheit, or nearly 80 degrees Celsius, through the material until its moisture content falls to around 6 to 8%. At this stage, the meat turns ivory yellow or light brown and becomes copra. The dried copra is crushed, heat-conditioned, and fed into an industrial screw press. A rotating steel screw compresses the material inside an increasingly narrow chamber, forcing crude coconut oil through small openings in the press cage. The remaining oil cake is cooled, ground, or pelletized for use as livestock feed, organic fertilizer, or biomass fuel. The freshly extracted oil is still cloudy and contains fine copra particles, moisture, and strong raw material odors. It is pumped into settling tanks, where larger solids sink to the bottom, before passing through filtration systems that remove smaller impurities. The oil may then be treated to reduce free fatty acids, pigments, and odor-causing compounds. Its moisture content can fall from approximately 0.67% to only 0.1%, making the oil clearer, more stable, and less likely to deteriorate during storage. Finally, the refined coconut oil is transferred into stainless steel tanks, ready for the soap base production stage. From the stainless steel storage tanks, the refined coconut oil is pumped directly into a reaction vessel and heated to approximately 140 to 160 degrees Fahrenheit or 60 to 71 degrees Celsius. A sodium hydroxide solution mixed with water is then gradually added according to a ratio calculated from the quantity of oil being processed. Inside the tank, large mixing blades continuously circulate the mixture, ensuring that the oil comes into uniform contact with the alkaline solution. The saponification reaction begins, converting the fats in the coconut oil into soap, while also producing glycerin. The initially clear and glossy liquid gradually becomes cloudy, thickens, and turns creamy white. The ingredient ratio must be carefully controlled. Insufficient alkali leaves some oil unreacted, while excessive alkali may cause dryness or skin irritation. Heating and mixing continue for approximately 2 hours until the material no longer separates and forms a thick, uniform soap base. Samples are then tested for temperature, pH, and residual alkali before the soap base is transferred to the drying stage. The crude soap leaving the reaction tank is still hot, soft, and highly viscous, so it cannot yet be milled or pressed into bars. It is pumped through a heat exchanger and sprayed into a thin layer inside a vacuum drying chamber. Water rapidly evaporates and carries heat away, causing the soap to cool, become more concentrated, and collect on the chamber walls. At this stage, the temperature of the soap mass may fall to approximately 95 to 104 degrees F. The material is then carried forward by a steel screw, compressed, and forced through dozens of small openings in a die, forming long, solid strands. On large production lines, a twin screw system can process up to 5.5 tons of soap per hour. Rotating blades immediately cut the strands into short sections, producing nearly uniform soap noodles. The soap noodles are weighed into batches, usually around 50 to 100 kilograms, and transferred into a stainless steel mixer. A dosing system then adds glycerin, moisturizing agents, colorants, and fragrances according to the formula. Inside, two sigma-shaped blades rotate in opposite directions, continuously gripping, crushing, and turning the entire mass. In only about 5 to 10 minutes, the soap particles are broken down and the additives are evenly distributed. Once the batch reaches uniform color, fragrance, and moisture, the discharge gate opens and releases the blended soap onto a conveyor for the next stage. The blended soap mass is still rough, loose, and filled with small air bubbles. It is fed into a milling machine containing 3 large steel rollers rotating at different speeds to pull and compress the material into thin layers. As the soap passes through the roller gaps, the rough particles are further crushed, while the colorants, glycerin, and fragrance are spread evenly throughout the entire mass. The thin layers then move into a vacuum plotter. Inside, 2 steel screws continuously carry the material forward. Air is removed while the soap is compressed and pushed through the extrusion die, emerging as a long, smooth, solid bar. Large machines can process up to 5.5 tons of soap per hour, equivalent to tens of thousands of finished bars. Sensors continuously measure the speed and length of the soap bar, then control a cutter that divides it into billets weighing approximately 3 to 5 ounces. Each billet is slightly larger than the finished soap bar so that there is enough material to fill the mold completely. Billets that are too short, misshapen, or underweight are recovered, ground, and returned to the plotter. The acceptable billets are placed between 2 halves of a mold. When the stamping machine operates, the mold closes with a force of approximately 25 to 36 tons on some models. The soft soap is pressed across the entire mold cavity, creating rounded edges and a smooth surface. The logo is not printed with ink. The brand name or decorative pattern is engraved in reverse on the mold surface, creating a sharp raised or recessed mark in a single stamping cycle. Every bar of soap must pass a final inspection before leaving the factory. Electronic scales check the weight, while high-speed cameras scan the surface for cracks, distorted edges, air holes, or blurred logos. Representative samples from each batch are also tested for moisture, hardness, color, fragrance, and residual alkali. A single measurement outside the permitted range can cause the entire batch to be held. Approved bars are sent into an automatic wrapping machine. Film or paper encloses the product, the edges are sealed, and the batch code and production date are printed. An industrial flowpack machine can package 350 to 400 bars per minute, equivalent to nearly 24,000 bars per hour. Finally, robots pack the products into cartons, stack them onto pallets, and move the entire shipment into storage, completing the journey from coconut to finished bar of soap. Coconut is not the only source of oil used to produce soap. Across vast fields, sunflowers are harvested approximately 30 to 45 days after blooming. Each flower head can contain up to 2,000 seeds. Combine harvesters equipped with cutting headers up to 40 feet wide can harvest approximately 15 acres per hour. The seeds are separated from the flower heads and cleaned using vibrating screens and magnetic separators, with a processing capacity of 20,000 pounds per hour. The seeds then pass through steel rollers that break their shells, are heated to approximately 160 degrees F, and are fed into a screw press. Pressure in the compression zone can reach approximately 10,000 psi, forcing the oil through the filtering openings. Sunflower seeds contain up to 38 to 50% oil and approximately 20% protein. To obtain 1 gallon of crude oil, the machine must still process approximately 22 pounds of seeds. The extracted oil is allowed to settle, filtered clean, and pumped into stainless steel tanks before continuing into the saponification line. From coconut oil to sunflower oil, every raw material must pass through a carefully controlled chain of processing stages before becoming the familiar bars of soap used in everyday life. The vegetable oils are cleaned, measured, combined with an alkaline solution, and transformed through saponification before being dried, milled, blended, shaped, and inspected prior to leaving the factory. Behind what appears to be a simple product is a precise combination of agriculture, chemistry, and mechanical engineering. From the speed of the mixing blades and the temperature inside the reaction vessel, to the ratio of oil and alkali and the remaining moisture in the soap base, every parameter must stay within a carefully defined range. Even a small deviation can cause the mixture to separate, leave part of the oil unreacted, make the soap too soft, or create excess alkali that affects the quality of the final product. What is equally remarkable is that many of the byproducts created along the way can be put to further use. Coconut husks can become ropes, mats, or growing media, while the remaining oil cake may be used in livestock feed, organic fertilizer, or biomass fuel. In this way, the production line does more than manufacture soap. It also creates a more efficient system for using nearly every part of the original material. From coconuts and sunflower seeds harvested in the fields to uniform bars moving along the final conveyor, this journey demonstrates how industrial technology can transform natural resources into an essential product used around the world. Which stage of this soap production line do you find the most remarkable? Share your thoughts in the comments and subscribe to Factron Process to continue exploring other fascinating manufacturing processes.